What they're asking you to do is to try to make composite functions out of these. So find two functions f and g such that f dot g of x equal h of x. Okay. How could we turn this thing into a composite function? Do you see anything in the function that kind of repeats itself? Big hint.
Oh.
Not that. What did you say? 80x plus something? X plus 4 repeats, okay. So if I'm trying to make a function out of this, what we want to do is to be able to say that this function right here is a composite function, where I'm going to plug something in. Remember, we plug the g of x, whatever's in here gets plugged in the function f of x, right? Well, if we thought of those x plus 4s as like something that got plugged in because we see them repeating, couldn't we say, okay, we're going to make the thing that gets plugged in, the g of x here, we'll make g of x be x plus 4. Because we see it, and it looks like it got plugged into another function. Possibly, what could our f of x be if we're going to plug g of x into it? What could it be? What would you have plugged it in here for? X squared, okay. It would have been like x squared plus 2x. This is how you could break something apart like this if you wanted to. Now, the reason we kind of look at this is sometimes in calculus, one of the big deals in calculus is it's easy, there are a lot of easy ways to integrate functions and differentiate them and stuff. But sometimes, if they're too complicated, we break them down into something simpler and we rewrite them. And so there's a little bit of this that goes on in calculus. It's just a little rewriting. Usually you think of it as substitution. But if you think of this, we could think of this as substitution too, because think of what if we wrote it now the way they wanted us to think of it. Well, we go, all right, f of x is the thing on the outside. It's the thing I'm going to be plugging something into its x, right? So we said our f of x would be x squared plus 2x, right? And then now we decided to make g of x this x plus 4 because it looked like it was getting plugged in certain places in the formula. So if we plug g of x now in for all the x's that were in the f of x down here, and I just, put them on the paper with parentheses so it'd make it easier for us to stick it in there, we could put the x plus 4 and the x plus 4, and we have the same thing that we started with. So you can break apart things this way. We don't do a lot of thinking like this in calculus, but there are times that we notice, oh, that thing inside, I could look at it as one thing that gets substituted into something else, and it'll make taking derivatives a lot easier when you do calculus. Just simple little substitution type tricks like this are things that make it easy to do things that look hard, okay? Now, when they give us the equation, we're always happy because that means we didn't have to figure it out. In this book, you're going to notice every time you get a word problem, pretty much they've done the hard work for you and they've given you the equation. And you do little happy dances when you actually have to start writing them. You're happy to see that they wrote it for you. And it says x is the speed of the car, miles per hour. And the distance in feet is okay, so where x is the speed of the car, miles per hour. So this is the reaction time. This R stands for reaction time. So let's kind of list what everything is so we can keep it straight. Because now we get another equation. And it's called b of x. Don't know why they couldn't have called it d of x, but because it represents the distance traveled while the driver is braking. So when you slam your brake on, that's your distance while braking. We get two equations here. We're going to find out later this year that when they give us two equations and they have the same variable in them, don't these both have the x in them, and x still represents miles per hour in this case, that we can call this is a parametric equation in disguise. It's two different functions written in terms of the same variable, and they're related to each other. And we could actually make more equations with them, and we'll do that a little bit this year later. Find the function, let's see, the distance of the driver's reaction time. Okay, this R of x, let me go kind of just modify a little bit. This is the distance traveled during reaction time. So you got your x is your speed per hour. R of x is your reaction time, and it's how far your car's traveling during your reaction time. You see something up ahead, your car's still traveling while you're seeing it and you're processing it, so you've gone a certain distance during that time, and then you slam on your brake, and then you're going to slide a little way longer while you're slowing down, or slow down. Hopefully you don't slide. Find the function that represents the total stopping distance. How could we describe the total distance? We have two distances here. What could you do to them to describe the total distance? Think about where you're in that car. What would you do if you knew your distance while you were seeing it and processing, and then you knew how long you slid? What would you do to find the total distance you traveled during that time? You just add them, right? Because you see it, you're kind of going, oh my goodness, so I'm going to have to stop, and you travel a little bit, right? Then you slam your brake on, and you go some more. Wouldn't you just add those distances together, right? So what we're going to do, if we want to describe the total distance, it would be the reaction time distance, which I'm just going to write as R of x. So it'll fit on the iPad. And then your braking distance. That would be your total distance, right? Couldn't I then just put the little expressions in that represent each equation, right? So R of x would be 3/4 x, and then B of x would be, that is showing, isn't it? Tell me if that's ever not showing. Y'all know I'm plus 115 x squared is our total distance. And they want us to call it t, so instead of calling it total distance, I'll call it t of x for total of x, okay? That's just kind of the things you do there. Yeah. So we graphed on the graphing calculator, and we have something that looks like this. I'll just kind of draw a rough graph of it because you can always put it on your graphing calculator. It does something like this. It is a parabola, but it's a very wide parabola. Why is that parabola that wide? Look at our equation here. Here's the x squared term. What's out in front of it? A fraction, and fractions make it much wider, so that kind of helps it make sense, right? Which term do you think contributes more to the magnitude of the sum at a higher speed? So let's say you're going 100 miles an hour. Which term do you think is going to make more difference, the 1/15x squared or the 3/4 x, bless you? Let's graph them both. Let's do this. On the same graph, I'm going to go to y equal, and I'm going to type in, let's go down here. We can leave all the graphs on the same line so we can actually test it and see. I know what the mathematical answer is, but it doesn't make sense to me either here, but I'm going to go ahead and well, let's look and see. We can see 3/4 x, okay, is one term, and the other term was 1/15x squared. So we could always do, they're asking us just to play around with it a little bit and think about what happens. I know what the answer is supposed to be. So once we get it there, let's graph it. So the red one was the 3/4 x, right? Yeah, this is a CE color edition. The x squared one was the black one that's showing up. Which one is having more of an impact overall? The 1/15x squared. That's okay. The black one seems to be more, it's climbing higher than the red one. Let's just verify that the black one was 1/15x squared. Yeah, that was, see how they got the color out front now on this one. If you've got a newer edition, this is a newer edition of those TI-84s. They put more memory in them so it could support color. A lot of the older ones just don't have enough memory in them to support color. So this one has color. And it's kind of nice just for, wow, that's a bad picture. Y'all should tell me it's that bad. Miss Carter,
I said I'm feeling blue.
I didn't realize. I had no idea. I thought you were just feeling blue. So the black graph was the 1/15x squared, and you could tell because up at the key, at the top where the functions are, you can see that's black. So the 1/15x squared contributed more. It had the higher exponent on it, didn't it?
Oh.
If I were to put this in general form, and one of the reasons we put things in general form is so we can just look at the term that's going to matter the most. If we were to write this in general form, and let's see, what do we want to call it? T of x, I think. We would say, oh, that's going way over time, I bet.